The second video is going to be primarily talking about what are called Eulerian graphs and Hamiltonian graphs. But to get started, I want to talk about different little walks is too specific, but little ways that we can travel along graphs, going from vertex to vertex. Now, I'm going to give you these definitions of a walk, a trail, a path, and a cycle. And then I'm going to show you some specific examples. So first of all, a walk. A walk on a graph is a finite, non-empty alternating sequence of vertices and edges of this form, okay? With vertices V, I, and V, and EI and E. So in other words, if I have a graph like this is A, B, C, D, and E, then I could write a walk on it. Now, frequently, what we'll do is we will omit writing the names of the edges, okay? Because they can be given by just giving two different vertices can define an edge. So a lot of times we'll just not write the name of the edges, and that'll be implied by the vertices. So I can write a walk on here. So these are the things. It's finite, so I'm not going to keep going forever. It's non-empty, so I have to go somewhere. Alternating means I go from one vertex to the other. I'm not going to repeat anything. So like, here's one, A, B, C. There's a walk. And that walk goes from the vertex A to the vertex B to the vertex C. That's all that I'm talking about. And in just a minute, I'm going to show you some more examples. But moving on, a trail is a walk that does not repeat any edges. It doesn't go over any edge more than once. A path is a trail that doesn't repeat a vertex. So a path is like a trail, but in addition to not repeating edges, I'm not going to repeat any vertices. The distance, which we're not going to do much with, but the distance between two vertices is the number of edges in the shortest path connecting them. And a cycle, and another term for this that we're going to use freely is a circuit. A cycle or a circuit is it's a trail where we only repeat one vertex, and it's the same one that we start and end on. So that's what a cycle is. It's we start and end on the same one, and that's the only one that is repeated. Okay, so let me show you some pictures and some examples of these. So here I have a graph drawn. It's called G with the vertices A, B, C, D, and E. And I want to illustrate walks, trails, paths, and cycles. Okay, so starting with walks. This would be an example of a walk. Start at A, go to B, go to C, and go to D. That's a walk. Here's another walk. A, B, A, E, B. That's a walk. Notice that I went over that edge more than once. It's still a walk. Now, let's think about things that are trails. And remember, trails have no repeated edges. So this would be not a trail. So here's a walk. Here's a trail. A, B, C, D. It's the same as that first walk that I did. All right. Another trail would be A, E, B, C, D, and back to B. That's fine. I can repeat vertices as long as I'm not repeating any edges. That's a trail. Now let's move on to paths. Okay, paths have no repeated vertices. So that first one is still going to be a path. That one I started with, A, B, C, D. That's a path. But since I don't have any repeated edges, this is not a path. But this would be a path, what I'm about to do. A, E, B, C, and D. Right? That one is fine. That's a path. And then finally, we have cycles. And cycles are basically, they're like paths, but I'm allowed to start and stop at the same point. Okay? My only repeated vertex is where I start and stop. So A, B, back to A, that's a cycle. Sometimes it's called a degenerate cycle because I'm going over the same edge right after itself. Another one would be A, E, B, D, C, and A. So this is a cycle, or again, this is called a circuit. Now, here's what I want you to keep in mind. The reason it's called a cycle is because it makes something that's kind of like a circle. You could imagine if we bend this out, we could turn that into a circle. That's where the name comes from. Okay, and again, this first one right here, this is sometimes called a degenerate cycle, and some textbooks you'll see, and some authors won't even call it a cycle at all. But there we go. That's the difference in walks, trails, paths, and cycles. Okay, now let's go back and look at some specific types of graphs. All right, moving on to Eulerian graphs. Basically, an Eulerian graph, and just for the record, the name comes from the mathematician Euler. It is not pronounced Euler; it is pronounced Euler. Who was very, very prolific. Did a lot of stuff in graph theory. So basically, an Eulerian graph is a graph that you have a trail. Basically, if you have a trail that goes through over all of the edges, and it's closed, so it starts and ends at the same vertex. So in other words, an Eulerian graph is one that has a closed circuit or cycle that goes through every edge. So an Eulerian trail or Eulerian circuit is a closed trail, that means cycle, that contains each edge exactly once. So it goes over every edge, and it doesn't go over any edge more than once. Okay? A graph like this is called Eulerian, or is called an Eulerian graph. So look at this one here on the left. This is Eulerian because watch. I'm going to start at this vertex. This is my starting point, and I can go over this edge, this edge, this edge. Now, notice I got to this vertex, but that's okay. I can go over the same vertex more than once, just not the same edge more than once. Then I can go along 4, 5, 6, 7, and then I'm at the end. So that is an Eulerian graph. Because it has an Eulerian circuit that goes through 1, 2, 3, 4, 5, 6, and 7. Now this one on the right is not Eulerian. Now in a second we're going to get a theorem that tells us some necessary and sufficient conditions. But let's just try. Let's try to draw an Eulerian circuit on here. So I'm going to start with this vertex, and by symmetry, starting with this one on the left would be the same as starting this one on the right. So I could either go up or down. So if I go up, and if I go down this way, then I have no choice but to go here. And then now it doesn't matter which way I go. I could go up, or I could go over to the left, and I would still have to repeat one of those edges to cover everything. So by that I mean, if I go this way, in order to cover the uncovered edge, I would have to either go over this edge again or over these edges again to get that one. That's not allowed. If, on the other hand, I went this way, in order to get this up and down edge, I would have to loop back over this one to go down, but that's not allowed. I would be covering the same edge again. Okay? So by symmetry, starting here at the left and going up or going down, the same thing would happen. Starting at the right, going up and down, the same thing would happen. So the only option we haven't looked at yet would be starting at either one of these ones along this vertical line. So if I start here, I could go down, and then if I go up then down this way. Sorry, my pen stuttered, and then back down. In order to get back where I started, I would have to loop over this edge again, which isn't allowed. So what if I went this way? Then I would go here, 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 and I would have to loop over that edge again. So basically, no matter which way you go, you're going to run into that issue. Loop back down again. So it's a neat little thing to kind of convince yourself and try all these different possibilities why that one cannot be Eulerian. Now, like I said, we do have a nice theorem that gives us necessary and sufficient conditions. So on the homework or on the test or something, if you're asked to explain why there is or is not an Eulerian circuit, well, you can cite these two theorems. A finite connected graph has an Eulerian circuit if and only if each vertex has an even degree. And a finite connected graph has an Eulerian path if and only if it has at most two vertices with an odd degree. So you can use that theorem whenever you're trying to decide whether or not graphs have Eulerian circuits or Eulerian paths. And I think I forgot to mention this, but an Euler path on a graph is a path that uses each vertex exactly once. Okay, it doesn't necessarily have to start and end at the same vertex. Okay, it just uses each edge exactly once. Now, a related idea is called a Hamiltonian graph, named after the mathematician Hamilton. Not related to the Broadway, the namesake of the Broadway production. That's a joke that probably will go over the heads of people in the years to come. All right, so Hamiltonian graphs. So a cycle in a graph is a Hamiltonian cycle if every vertex except for the starting and ending vertex is visited exactly once. A graph is Hamiltonian or a Hamiltonian graph if it has a Hamiltonian cycle. So the difference in an Euler graph and a Hamiltonian graph is, in the Euler one, you go over each edge exactly once. In the Hamiltonian, you go over each vertex exactly once. Okay? So that's the difference in the two. So here on the left, we have a Hamiltonian graph, and here's the Hamiltonian cycle. It's given to us right here. So now remember, I'm trying to visit each vertex exactly once. So I'm going to start at A, then go to B, then go to C, then go to D, and then go to A. Now, this vertical line has not been visited. That doesn't matter because all I care about is that I hit each vertex exactly once. Doesn't matter if I hit all the edges or not because these are Hamiltonian graphs. So as for this one on the right, it is not Hamiltonian. So let's see what happens if we try to draw a Hamiltonian cycle on here. So I'm going to start with this bottom vertex, and by symmetry, that would be the same as starting at the top, so I can eliminate some possibilities. Well, I only have one choice. I have to go this way and get to this vertex. Now, if I go up and to the left, I hit this vertex. So now I don't have a choice. I have to go down here. Then I can't go this way because I would be ending up where I started before I covered all of them. So I have to go over here. But now, to get back where I started to make it a cycle, I'm going to have to either revisit this vertex or revisit that vertex. Neither one of those are allowed. So what else could we try? I could try going up here, and then if I go this way, and then this way, and then up here, well, to get back where I started, again, I'm going to have to go somewhere I've already been. What if I start over here? I can go down, and then up, and then this way. And to get back where I started, again, I'm going to have to hit a vertex I've already hit. I could go down, and then up, and then down, and then over here. And same thing's going to happen. So you'll find that no matter what you try, something like that is going to happen. So here is a big difference between graphs that are between Euler graphs and Hamilton graphs. We have the Euler theorem to tell us whether graphs are Euler. I'm just going to say Euler graphs, whether they're an Euler graph or not. We don't have a similar thing for Hamilton graphs. Okay, we do have sufficient conditions. This is a theorem due to the mathematician Paul Dirac. A simple graph with greater than 3 vertices is Hamilton if every vertex has degree greater than or equal to n over 2. So this isn't as great a situation as we would like to be in, but it can sometimes tell us when we have a Hamilton graph. Okay? All right, one more thing. Actually, no, I'm not going to do that now. The notes, which I'm about to show you, go over trees, and that this isn't covered in the exposition part of the book, but this exercise 3 or exercise 10 here does talk some about trees, but I'm going to go into more detail about that when we go over the notes, which we're going to do right now. I do have a few things I want to point out in the notes, other than just the usual that, you know, this is summarizing stuff about walks, trails, circuits, and all that stuff. There are 2 topics that I want you to be familiar with that I didn't talk about in the other part of the lecture. The first is connected, okay? A graph is connected if there is a path from each vertex to every other vertex. So, for example, here, if I start at the vertex A, then I can draw a path that goes to every other vertex. So this is called a connected graph. But this one here on the right, okay? Now what I'm doing here is I'm considering this to be one single graph. In that, if I call this the graph G, my vertex set is going to be the vertices A, B, C, D, E, and F. And then my edge set is going to be the edges AB, AC, BC, but that's not all. I'm also going to include ED and EF and DF. Okay, so this is still one graph. There's just 2 different pieces there. Okay? So this graph is not a connected graph. And if I start trying to connect vertices with paths, I can go from A to B to C, and that's all. Then if I start trying to draw a second path, I can go from E to F to D. So this graph has 2 connected components, okay, because there's 2 different pieces of the graph, okay? And, you know, as always, watch the video. Videos are really helpful. The other idea that's in the notes that's important is the idea of trees, okay? A tree is a connected graph with no circuits, okay? So you think of it as like, this is the general idea right here, where we have the root and the trunk grows and we have branches spreading out. So there are no cycles, okay? There are no cycles whatsoever. These are all examples of trees. And a group of disconnected trees is called a forest. So, for example, if I just draw this graph, that's a tree, okay? It's also a forest because it's a group of disconnected trees. It's a group of 1. If I consider these 2 graphs together, all right, this is not a tree, okay, because it's not connected. It is a forest, okay? If I consider this as a single graph, it's not a tree because it isn't connected. However, it is a forest because it's a group of it's a group of trees. All right, so watch the video. Trees are really useful because we have this idea of a binary search tree. A binary search tree has the property that nodes to the left contain smaller values than nodes to the right. Okay, nodes to the right contain higher values, and you know, larger and smaller could mean numerically larger, as in this example. I have 25, and to the left I have things that are smaller, 20. To the left I have 10, to the left I have 5. But if I look at 10 right here and go to the right, well, then I have something larger than 10. If I look at 20 and go to the right, I have something larger than 20, which is 22. And then if I go to the right, everything on this side of it is larger than 25, and the tree breaks down again according to larger and smaller. I can also have alphabetical binary trees where the larger and smaller ordering is given by lexicographic ordering or alphabetical ordering. So watch the video on binary search trees. It's really useful. Then we have, summarizing stuff about graphs, Euler graphs, a nice video on the bridges of Königsberg, which was a motivation for a lot of graph theory. Existence of Euler circuits, same thing with Hamilton cycles and Hamilton circuits. And then we have the practice problems, which we're going to look at right now. All right, looking at these problems, number one, does each of the lists of vertices form a path in the group? Which of them are circuits? Remember what a path is? It's does it have any repeated, no repeated vertices? Well, since there are no repeated vertices allowed, this one, whoops, that is all bulky. Let me change the size. This is not a path because I have repeated vertices. This one is not a path because there are repeated vertices. This one is also not a path because there are repeated vertices. However, those may still be cycles, circuits. Let's see. As far as A goes, let's just trace through it and see what happens. So A to E to B to C and then back to B. Whoops, you know what? I didn't notice that there are repeated vertices there. So this is not a path. It's also not a cycle or a circuit because it doesn't start and end at the same one. So not only is that one not a path, it's also not a circuit. So let's look and see if part B is a circuit. I start at E, I go to B, I go to, oh, look, I can't go over to A, right? I don't have an edge taking me over to A. So just because you have a list of vertices, that doesn't mean that's going to give you a path, a cycle, certainly not even a path. The edges, those edges also have to be in the graph. So that's the theme that I'm going to hit on a lot, as you'll see in just a second. If I try to do this one, I'll have A down to E, back to A, D, B, C, and look, I can't go back to A. All right, so this is not a circuit, not a circuit. For the last one, part D, what happens? Well, we start at C, go to D, can't even go to D, right? Can't go over there. So this one is also not a circuit. Okay, so again, what I'm trying to stress right here is just because you have a list of vertices doesn't mean that defines a circuit or a path or a walk or anything, because the edges that it's wanting you to cross over have to actually be in your graph. Okay, so next one down, number two, determine whether a given graph is connected. If it is, how many connected components does it have? That is, if it's not connected, rather, how many connected components? So we're going to consider this whole thing to be one graph. So starting here, I'm going to use different colors for the components. So that's all of the vertices that I can connect in blue. And then these are all the ones that I can connect in that pinkish color. That's that one by itself in yellow. So that tells me that there are 3 connected components. All right, let's look at part B rather. So I'm going to start right here and just see how far I can go. I can go here and I can get to here. I can get to here and here and here and here and here and here and here. Then I can go back to here and go down to here. So like this is connected. This one is connected. This Star of David, or 6 6-pointed star. 1 connected component. Oh, look. And even though they overlap and it looks like there's only one piece there, there are actually 2. Because I have to get a second color in order to color all the edges. So this one actually has 2 connected components. All right. Number 3, let's determine whether these are trees, forests, or neither. Okay, so we're just looking to see if there's any cycles in here. So for A, like I can cover all of my vertices, and I didn't get back to where I started. So even though it looks like this right here, it looks like a circle or a triangle in there, there's no vertex in the middle, so there's no cycle. So A is a tree, and it is a forest because all trees are forests. Okay. Part B, I can go here, go around, and look, that's it, I'm done. Again, even though it looks like there may be some, there are no cycles in there because I didn't end up where I started. So this is a tree, and it's also a forest because every tree is a forest. For part C, I can go from here to here, and that's all of the ones that I can color in blue. So if I try using this pinkish color, that's all of them. So it's not connected. So this is not a tree because it's not connected. However, it is a forest because it's it's a group of trees. And this last one, I think it's pretty clear here that there's no cycles in here. So this is a tree and it's a forest. Okay. Number 5, which of these have Euler circuits, which have Euler paths? Well, remember the theorem that there's an Euler circuit, a graph has an Euler circuit if and only if each vertex has even degree. And there is an Euler path if and only if there are at most 2 vertices. Misspelled that. 2 vertices with odd degree. So let's just check those conditions, okay? A, let's see, this vertex has degree 2, this one has degree 2, this one has degree 2. So the corners all have degree 2, these ones in the middle, 1, 2, all have degree 4. This has degree 4, degree 4, degree 4, degree 4. So it looks like they all have even degree. So yeah, there's an Euler circuit. Euler circuit, check. Okay. Let's look at the next one. Oh, look right here. This has odd degree. So Euler circuit, no Euler circuit. And this one right here, 1, 2, even degree. This one has even degree, even degree, even degree, even degree. 4, that's 4. So yeah, these all have even degree. So there is an Euler circuit, check. Now I need to see how many odd degree vertices there are. Well, this one has no odd degree vertices. They're all even. So that means there is an Euler path, because remember the conditions are, it's an Euler path if it has at most 2 vertices with odd degree. That means it can have none, it can have 1, or it can have 2, and there's still an Euler path, as long as there is at most 2 vertices with odd degree. So this one has none, so there is an Euler path. Let's look at this one. How many odd degree vertices do I have? Well, here's 1, 1, 2, 3, here's 1, 1, 2, 3, here's 1, here's 1. So no, I have too many vertices that are odd degree. And this one, we checked it before, and every vertex had even degree, so that means there is an Euler path there. And this last problem, determine whether these have Hamilton circuits or Hamilton paths or neither. Remember, a Hamilton circuit means it visits every vertex and starts and ends on the same one. And a Hamilton path means it's going to visit every vertex with no repeats. So, I know we have that theorem that tells us sometimes when we can figure it out, but let's just see if we can draw them. So Hamilton circuit, or reason why there isn't one. Hamilton circuit for B and Hamilton circuit for C. Okay. Oops. So let's just try to make a Hamilton circuit. So if I start at B and I go here and then here, if I go across, then I'll have to repeat a vertex before I can get back to where I started. So that's not going to work. So starting at any of these outside points, A, B, D, or E, that's going to happen, okay? And then if I start at C and go down to B, up to A, well, I'm going to hit C again before I get any of these. So no, there's no Hamilton circuit there by that type of reasoning, okay? In the next one, let's see, I'm going to start here and go boom, 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 boom. There's a Hamilton circuit. I did it. Start with this one. So if I start at this point out here by itself, you know, and then start going over, you know, in order to get back to that point F, I'm going to have to repeat over E. So that's not going to work. So the only option is to start at one that, you know, that isn't F. So, you know, if I start at E, if I go to F, well, I would repeat going back here. So I can't go to F. So if I go to a different one and do this, in order to get to F, I have to hit E again. So maybe, you know, maybe I can start somewhere else and not do it that way. But if I start at any other point, like at B, I have to eventually get to E and then go to F. But then to get back where I started, I have to go over E again. So no, there's no Hamilton circuit for this graph. This graph doesn't have a Hamilton circuit. Okay? So now let's talk about Hamilton paths. And in this case, I don't have to get back where I started, but I do have to hit each vertex. Hamilton path. So let's see what happens if I try that. So I can start here, boom, 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 check. Right? I hit every vertex. Since it's a path, I don't have to get back where I started. So that does have a Hamilton path. This one is also going to have one. There's a circuit, so all I have to do is stop before I do that repeat. So check. And then here I can do this. And I got all of them. So that one also has a Hamilton path. So as you can see, Hamilton paths are much easier to have than Hamilton circuits. And they're easier to show. All right, that's it. That's all the examples. So there you go. Again, you know, read through the notes, watch all those additional videos, and I will talk to you later.